a larger symmetry algebra that supersymmetric theories sometimes enjoy invariance under. Okay? And this larger symmetry algebra is sometimes called the superconformal algebra. So, in the first part of today's class, we will talk a little bit about just the conformal algebra, and then we will discuss the later part of the class. We will discuss the superconformal algebra. Okay. So, what is conformal symmetry? Okay. As you know, quantum field theories are one really useful way of thinking of the space of all quantum field theories is to arrange quantum field theories, to understand quantum field theories by studying the renormalization group flow. Quantum field theories, one definition of quantum field theory, is a theory that is defined by an RG flow that starts at some UV fixed point and then goes away from this UV fixed point by some sort of, there's a relevant operator that takes you away from this UV fixed point. Okay, so the space of all quantum field theories can be thought of as this way. There are these special quantum field theories which are fixed points of the renormalization group. And all other quantum field theories, by quantum field theory, I mean something that is well defined at all energy scales. Okay, all other quantum field theories are described by flows away from these fixed points. These flows can be interesting. They can go off to strong coupling, like QCD, or they could go to another fixed point, like, I don't know, the RG flow from a theory of free scalars to Wilson-Fisher fixed point of 3 dimensions. Or they could go to a massive theory, like most RG flows do. Okay, they could do various possible things, but they all start in these fixed point things. Now you could ask, why did they start in these fixed point things? This is the answer, roughly speaking, is this is the only way we have found so far, apart from string theory, which includes gravity, of making the theory well defined to arbitrarily high energies. Typically these theories, if you go to higher and higher energies, often a theory will start violating unitarity, unless the behavior of the theory changes appropriately. And fixed points governing the high energy behavior ensures that all the good features of quantum field theory, like unitarity and so on, preserve to arbitrarily high energies. Okay? So at very high energies, theory governed by a fixed point ensures that the theory is well defined at all energy scales. Okay? And then quantum field theories are defined by taking these fixed points, which govern the very high energy behavior, and looking at relevant deformations that flow away from these fixed points to give you more general quantum field. Why did I say all this? I said all this because you see here that in the space of quantum field theories, there is a very special set of quantum field theories, namely the fixed points themselves. Those are very special. In some sense, they are the mother of all theories. You know everything about them. In principle, you know everything about all quantum field theories, because all quantum field theories are defined as renormalization group flows away from these fixed points. Okay? So clearly, these fixed points are interesting because they form the basis for the definition of the set of all quantum field theories. They're also interesting for another reason. They also govern generic low energy behavior in vicinity of theories that have very long range interactions. All this you know, right? Right? So fixed points are important for defining theories, field theories in the IR, in the UV. They're also important because, in the neighborhood of phase transitions, for instance, they govern universal behavior. Okay, so these fixed points are very important theories. Now, what is special about a fixed point? Well, the first thing that's special about a fixed point is this, that under the renormalization group flow, this theory does not flow. It's a fixed point. Now, renormalization group flow is changing scale. So the first thing, the obvious thing about fixed points is that they're scale invariant. Okay? Now, from the point of view of the symmetry of symmetries, we're going to be studying Lorentz invariant theories. So these theories have generators P mu and M mu nu, like all Lorentz invariant theories have. What we've just said is that they've got a new generator, which I'm going to call D, a new symmetry. The symmetry of that generates scale transformations. Okay? How do these scale transformations, how do they act with these p mu's and m mu's? Well, p mu is generated by d mu, and so d counts dimension, mass dimension. So we expect that d commutator p mu is equal to p mu. There may be some i's. I'll get factors of I straight in 2 minutes. Okay? On the other hand, what about d with m mu nu? Well, m mu nu was x mu del nu minus x nu del mu. There's an x for every del. So it's scale invariant. Right? So d commutator m is equal to 0. This is what we expect. And and d, of course, commutes with itself, like every operator commutes with itself. So these supplemented with the usual Lorentz transformation commutation relations give you the relationship of a new symmetry algebra, one in which you've appended scale transformations to Lorentz algebra. Sounds pretty boring, right? Nothing interesting is happening. Which one? D and P? See, this guy is a derivative. So it's mass dimension 1. This guy is x times derivative. So it's mass dimension 0. Right? M just acts on angles, right? So it doesn't have any mass dimension. Okay? Whereas P moves you in space, right? It moves a certain distance. That distance has a unit. Okay? Clear? Okay.
Oh, you're saying mass dimension comes in front of the incomplete.
Of stuff, yes. Because D is scaling, right? Right? Okay. Now, had this been the end of the story, it would have been a pretty boring story. However, what we have observed is that typically, and in some situations sort of always, okay, in some situations always, this is never, okay, let me make a more careful statement. In 2 dimensions, this has been, what I'm saying has been proved. In higher than 2 dimensions, a lot is known about this. I mean, it's believed to be true, but nobody, I think, has really ever proved the statement. Okay? But typically, what happens is that at fixed points of the renormalization group, at least if the fixed point is non-trivial, so that it's not some free theory in some way, this symmetry algebra is enhanced to a bigger symmetry algebra, one that has these generators, but has a new set of generators called conformal generators. Okay? So I'm going to write down, this is, it's believed that we will one day be able to prove the statement in general, that in any non-trivial fixed point of the renormalization group, the actual symmetry algebra is more than just translations, rotations, and scale transformations. It actually includes bigger algebra. Okay? Like I say, in 2 dimensions, there is a proof, at least a more or less proof. It's basically Polchinski. Okay? In higher than 2 dimensions, certainly believed to be true, and people have tried hard to. There was a paper by Komargotsky in which there was both a proof and a counterexample. People believe it to be true, and the I's and T's have not been dotted and crossed. Okay. So I'm going to introduce you to this conformal algebra, tell you a little bit about it, and so we'll get a little bit used to this algebra. So first, let me write down the algebra in detail. Okay, the reference I'm following for this lecture is a paper I wrote in last century, 1997. It's called Restrictions Imposed by Superconformal Invariance on Quantum Field Theories. Okay, so the references. Okay. Just so that we have it once on the board, I'm just going to write down the full commutation relations of the conformal algebra. Okay. Okay, this is the usual Lorentz transformation commutation relations. This you're very familiar with. Okay, what about mu nu with p alpha? This, of course, also you know. It's the statement that p is rotated like a vector, right? And the minus I is some convention of what I've chosen the generators to be sort of Hermitian, you know. Mu alpha p. D with mu nu is equal to 0. We've seen this before. Okay. M mu nu, and now we get to all the new stuff. Okay, first D with p mu nu. D with k mu. Now, this is the new thing. There is a new set of generators which are vector under Lorentz transformations. These are called conformal generators. Okay? And D with q mu is equal to minus I, minus k mu. This tells you that just like P had dimension 1, eigenvalue 1 under the dilatation, minus I is there behind it. This has dimension minus 1. Okay? Of course, D with D is 0. P with P is equal to P mu, P nu is equal to K mu, K nu is equal to 0. And the most non-trivial commutation relation is this. Okay, the commutator of P with K is a linear combination of the metric times the dilatation plus a rotation. Okay, now I want to get to know, I would like you to get to know this algebra a little bit. So we'll do one or two little exercises with it. The first thing is this. One way of generating this algebra is through differential operators acting on functions. Okay? So I'm going to write down what differential operators acting on functions generate this algebra. Okay? So if you do this, if you say m mu nu is equal to minus I x mu del nu minus x nu del mu. The usual things, right? P mu is equal to minus I del mu. D, any guesses to what D is? Into minus x dot del. minus because we're counting mass dimension, not position dimension. Okay? Obviously, that's measuring homogeneity. Okay? Oh, but, and this is the interesting thing, k mu is equal to minus I into minus 2 x mu into x dot del plus x square to del mu. Minus 2x mu into x dot del minus x square into del mu. Okay? If you put these generators, you treat these as vector fields and you compute their commutator, unless I've messed up, you will get these commutation relations. Okay? So one way of implementing these commutation relations is as vector fields acting on functions. Okay. Now, so far you're thinking all good, but all I've done is write down some commutation relations. What's going on? Where did they come from? Okay? So the physical motivation for this set of commutation relations comes as follows. Notice that when a theory is scale invariant, okay, it's independent of scale. Which means that if you take the theory and have it defined on a space with metric G mu nu, or you take the theory and have it defined on the space with metric G mu nu times e to the power 2 phi naught, where phi naught is some constant, you get the same answer. Right? Because all that changing the metric by constant does is change all lengths. But the theory was invariant under that. You may have to transform a few quantities with some powers of phi naught. Okay, everything with some dimension will pick up the appropriate powers of phi naught. But apart from that scaling, the theory is invariant. That's what it means for a theory to be scale invariant. Now you could ask the following. Suppose I did the following. Suppose I take G mu nu and take it to e to the power phi of x times G mu nu, where phi is some function of x. Okay, such a transformation has a name. It's called a Weyl transformation. So you change the metric of on which the theory is defined. Okay, you change the metric on which the theory is defined, but not in the most general way. Just by an overall rescaling, which is allowed to be position dependent. Such a transformation is called a Weyl transformation. Now, you might ask, could it be? Okay, could it be that this theory is invariant under this more general kind of transformation?
These are not diffeomorphisms, right?
These are not diffeomorphisms. We're changing the metric. Okay, we've got one metric, we multiply the metric by this thing.
And then we compare the correlation functions with the same points.
With the same points, and maybe we need to scale quantities. Okay, exactly. Now, the remarkable thing is that up to some anomalies and so on, small anomalies that we will discuss as we go along. Fixed points of the renormalization group are believed to be invariant under this bigger scaling. Under this bigger scaling, okay, up to some small issues. Okay? Now I want to convince you that this statement is equivalent to being to invariance under this larger conformal algebra. Okay? Why is that the case? You see, Chintan asked the key question for this. I have said that suppose we have a theory which is invariant under G mu nu goes to e to the power 2 phi of x times G mu nu. Now, when we talk about the invariance of a quantum field theory, okay, when we talk about the invariance of a quantum field theory, we talk about the invariance of a quantum field theory on a given background metric. Saying that a quantum field theory with one metric, same as a quantum field theory in another, is an interesting statement. But it's not an invariance of the quantum field theory in flat space. If we're in flat space, why do we care about some other metric? Okay? But note the following. Suppose you can take some metric, let's say flat space. So take eta mu. And we can do some coordinate change. So that under this coordinate change, this metric goes to eta mu nu times zeta of x. Because of coordinates change now, okay, in the new coordinate the metric picks up this form. Now, because the theory by assumption is Weyl invariant, okay, then the theory in the new coordinates and metric eta is the same as the theory in the old coordinates and metric eta. Okay? So if you can find a set of coordinate changes so that under these coordinate changes the metric may change, but it changes only up to an overall factor, then if the field theory was Weyl invariant, then those coordinate changes will represent symmetries of this theory. What are the simplest such coordinate changes? The simplest such coordinate changes are coordinate changes under which the metric just doesn't change. Those are generated, as you know, by killing vectors. But what are those? In flat space, those are Lorentz transformations. M mu nu doesn't change the metric. P mu doesn't change the metric. Is this clear? So, the simplest version of the statement we're very familiar with. Any coordinate change that leaves the metric unchanged is a symmetry of the theory if this is Lorentz transformations. Okay? But now we're saying that if the theory is more special than just Lorentz invariant, if it's Weyl invariant, then any coordinate change that does more than leave it unchanged, that changes it, but only in this very special way, that changes it only up to an overall scale factor of the metric, that will also be a symmetry of the theory. Okay, so now let's try to write that down in some sort of equation. It's always easier to deal with infinitesimals rather than finite things. So let's make this condition some sort of infinitesimal condition. Any coordinate change is described by a vector field infinitesimally, because x mu goes to x mu plus epsilon times v mu is the infinitesimal coordinate change. So we've got some vector field. Okay? How does a metric change infinitesimally under the change given by this kind of vector field? All of you know this famous formula, right? The famous formula is delta G mu nu is equal to del mu v nu plus del nu v mu. And maybe I'm missing some half and 2 and so on, proportion of 2. This is familiar, right? We're working in flat space. So del is proportional to del mu v nu plus del nu v mu. Okay? So the condition that we want to put is that we're going to search for vector fields so that if we wanted an invariance, we will be looking for killing vectors. The killing vector condition is that this is 0. Doesn't change the metric. It's a killing equation. Okay? The condition that we want to put instead is that del mu v nu plus del nu v mu is equal to some number we don't know about, something that could be a function of position, alpha times eta mu nu. If this is true, then a Weyl invariant theory will be invariant under such coordinate changes. Okay, but now if this is true, we can easily find what alpha must be. How do we do that? Just contract indices on both sides of this equation. Here we get 2 del dot v. Here we get alpha times d, where d is space-time dimension. And therefore, alpha is equal to 2 del dot V divided by D. And therefore, this equation can be simplified to del mu V nu plus del nu V mu is equal to 2 del dot V divided by D times eta mu. These are the infinitesimal transformations which, if it changes the metric at all,
It will change by.
changes it only by something times the metric. That something is allowed to be position dependent.
Yeah.
As we see this V here.
But this is constant.
This is the mathematical equation we have to solve to find all such coordinate changes. We have to find the solutions to the solution to this equation.
Sorry, then what is the statement?
Any solution to this equation defines a coordinate change that will be a symmetry of a theory. Okay? Chintan?
Can you repeat that argument about how this coordinate changes?
How the coordinate changes is symmetry? You see, first we perform a coordinate change. The coordinate change in a diffeomorphically invariant theory, as we're assuming is always the case, causes always a symmetry. The problem is it changes the metric. Any coordinate change is a symmetry of the theory, but it takes a quantum field theory in one metric to a quantum field theory in another metric. This is not what we normally call a symmetry.
But
Tell.
it's the same metric, right? It's just diffeomorphism. Why are you saying
It's not the same form of the metric. So you see, the Lagrangian in one set of coordinates is one Lagrangian. Lagrangian in another set of coordinates is another Lagrangian. Right? This is a triviality. This is just a change of variables.
So you see, TIFR depends on every coordinate system.
Meaning, you solve the theory in one coordinate system, you can solve it in every other coordinate system just by doing this change of variables.
Yes.
Okay? However, if you wanted the form of the answer of the correlations in the new coordinates, it will take a completely different form in general from the form in the old coordinates. It's not like the correlator in new coordinates will be correlator in old coordinates up to some scale. Right? That's what we normally mean by symmetry. Okay? This is not a symmetry, it's a triviality.
Correlation functions will have that symmetry so that it remains invariant. Like, they look exactly the same.
The form in the new coordinates is different from the form in the old coordinates in general. However, now if we perform the kind of coordinate change that changes the metric only by an overall factor, and the theory is Weyl invariant, then the form of the correlator in the new coordinates will be the same as the form in the old coordinates. This is what we mean by symmetry. Like the statement that correlation functions only depend on cross ratio. Understand? Okay? Yeah, so it's very important to distinguish trivial things from interesting things. Changes of variable are trivialities. Changes of variable that leave the action unchanged in form are not trivialities. This is the whole point of the proof of Noether's theorem, for instance. For instance, very similar analysis. In a path integrity, you can always make a change of variables. That's a triviality. But changes of variables in which the action takes the same form in the new variables as in the old variables, that's not a triviality. That has consequences. Okay? A very similar kind of thing. Okay? Excellent. So, this equation has a name. This is called so this equation of course had a name. So, del alpha mu v nu plus del nu v mu is equal to 0. If the symmetries of a general quantum field theory, it's called the Killing equation. Anyone who studied general relativity would have encountered this Killing equation somewhere. Solutions to these are called Killing vector fields. Okay? This has a similar name. It's called the Conformal Killing equation, CK. And solutions to these equations are called conformal Killing vectors. Solutions to the first equation are called Killing vectors. Solutions to these equations are called conformal Killing vectors. Why are conformal Killing vectors interesting? For many reasons for general relativists. But for quantum field theory, the most important reason is this. That if your theory was Weyl invariant, then conformal killing vectors represent infinitesimal symmetries of the theory. Okay? So now there is an important question. Can we find all solutions to this equation? Okay? It's not a hard job actually. People have very sophisticated ways, but I remember when I first encountered this equation, the way I did it was to just write down the most general Taylor series expansion of V, plug it back in, and you can easily come by the solution. Okay? I'll leave this for you as an exercise. Okay? There are also sophisticated, now when you know the answer, there are always cheap trick ways of getting it. But, okay, fine, you can find the answer. The important thing about the answer is the following. The answer is different in 2 and every other dimension. Please go ahead.
So is it the fact that it's a space-dependent Weyl factor and not a constant Weyl factor?
Where is that fact?
Where is the fact that it's not a constant
Weyl factor? That's in this. If V is a linear function of x, then this, which is playing the role of the Weyl factor, would be a constant. Okay? And that is the case for rotations. In fact, the constant for rotations will be 0. It will turn out, because this part will cancel this part. Okay? But that is also the case for dilatations. Okay? That is not the case for the conformal killing vectors, because this is quadratic. So after taking one derivative here, you'll still be left with something depending on x. This is the infinitesimal Weyl factor. Is this clear, Sunil?
Just one question.
Go on.
The way you said to solve the equation,
Yes.
it is good for returning, but not for any general.
That's true. That's true. That's true. You would have to work harder for some general. Of course, there are zillions of ways to solve this equation. I'm just saying that some ways require cleverness, and some ways are systematic.
In many cases, things are related to invariance, so
You can do it. Yes, yes. But just for flat space, if you don't want to believe somebody's cleverness, write down a Taylor series, solve it. You'll also see the difference between d equals 2 and d higher than 2. So, but let me tell you the answer. Let's first look at d equals 2. D equals 2, of course, is very simple. Okay? Let's look at d equals 2. Okay. So in d equals 2, this equation is what? It is, first if we just write it down in, let's do what will help us. Let's write it down in complex coordinates, in z and z bar coordinates. Okay? In z and z bar coordinates, this guy here has, eta has only a z bar component. Okay? So on the left hand side, two equations become very simple. Del z vz is equal to 0. Because del z vz plus del z vz is equal to 0. But mu and nu are both z. And del z bar vz bar is equal to 0. Okay? On the other hand, you get the following equation. You get something like del z vz bar plus del z bar vz right? If you are doing z bar is equal to, and now you have to del dot v, 2 and 2 cancel. Now you have to keep your factors of 2 carefully. But you know del dot v is del mu v mu. Okay? And therefore is, these indices contract, but when you lower, they off contract. Okay? And when you keep track of all the factors of 2 carefully, this just is del z vz bar plus del z bar vz. So this equation is not an equation. It's an identity. It's just identically true. Okay, so that last equation was just saying nothing. Okay, the first equation tells us that Vz is anti-analytic, or if we take V, this is Vz is a function of Z. The second equation tells us that Vz bar is a function of Z bar. Okay, and therefore you find that every analytic. Oh, I raised an index. Okay, every analytic vector field is a solution, and every anti-analytic vector field is a solution. Vz is a function of Z is a solution. Vz bar is a function of Z bar is a solution. Infinite number of such solutions. This, of course, is not a surprise to any of you. Certainly those who were in my string theory course, we studied it for a year, right? Okay, these are the famous conformal transformations of two-dimensional field theory. And those who've studied 2 dimensions or studied string theory might tend to think, okay, conformal transformation is huge symmetry, infinite dimensional conformal symmetry algebra. That is not true in D higher than 2. In D higher than 2, if you study solutions to this equation, you will find that the only solutions are these guys. Not hard to check all of these solve that equation just by plugging in. And not too hard to convince yourself that there are no other solutions. Okay? So in D higher than 2, the conformal algebra, the symmetry algebra of theories that are invariant, that enjoy invariance under Weyl transformations. Okay. In D higher than 2, the symmetry algebra of theories that enjoy invariance under Weyl transformations is a finite group. Okay? Then it of course includes the Lorentz algebra. Of course it includes scaling dimensions, but includes one additional element. That's this K mu. Okay? What is the analog of this K mu in 2 dimensions? Well, as you know, the 2-dimensional conformal algebra, the 2-dimensional algebra, this Virasoro algebra, has an SL2R times SL2R subgroup. This SL2R has no central charge. This subgroup is special for various reasons, one of which is that it's the largest subgroup in which the central charge does not appear on the right-hand side of the algebra. Okay? That SL2R times SL2R is the analog of this group here. Okay? For in 2 dimensions, let's do some counting. First, let's count how many generators there are here. Well, there's D into D minus 1. That's Lorentz transformations. Plus 2 times D, that's momenta and special conformal transformations. Plus 1, which is dilatations. Now this, by 2x. Okay, now this is the same, I'm claiming, as D plus 2 into D plus 1 by 2. Let's check the factor of D. This D comes with a 1 and a 2, so 3 by 2 here. And it's 3 by 2? Yeah, 2 minus half. What about the factor of 1? That comes with a 1 and that comes with a 1. So that works. Okay? So what does this amount to in D equals 2? Well, in D equals 2, it's 4 into 3 by 2, so that's 2 into 3, so that's equal to 6, which is the same as the number of elements in SL2R times SL2R, which is 3 plus 3. Okay? So SL2R times SL2R is the analog of this, it's sometimes called the global part of the algebra in 2 dimensions. It's the analog of the conformal group in high dimension. The full Virasoro algebra has no analog in high dimension. Okay? Great. So, this is the first thing I wanted to say about it. Physically, what does this algebra mean? Okay. Now, the second thing I want to say about it is mathematically, what does this algebra mean? Okay, what do I mean by that? I've given you some commutation relations, okay, and that defines an algebra. But, you know, you might ask, fine, you give me some commutation relations, but do these commutation relations fit inside some group that I'm familiar with? The answer in this case is the following. This is sort of suggestive, right? It suggests, it tells you that the algebra has as many elements as SOD plus 2 would have. But clearly it's not SOD plus 2, because even the Lorentz part is SOD comma 1, sorry, SOD minus 1 comma 1. So, but you might think it might be some complex version of SOD plus 2. Claim, this algebra in fact is SOD comma 2. Now these commutation relations I've written down are in fact the commutation relations for SOD comma 2. Okay, now to convince you of that claim, I would have to tell you how I can identify the standard elements of SOD comma 2 with these guys. And I will tell you how that works. Okay, so let's call SAB. Let SAB denote SOD comma 2 generators in some standard basis, right? So in a basis where the commutation relations are like the first line of there, except that eta has D pluses and 2 minuses. Okay, and let the indices A, B run from -1 up to D. So minus 1 and 0 are the two negative indices, and 1 to D are the D positive indices. I think I've been calling it capital D. So. Okay, then the identification is as follows. S mu nu is equal to m mu nu. Mu nu indices run from 0 to D minus 1. Okay, every instance of D or minus 1 I will say explicitly. Okay, S mu nu is M mu nu. S minus 1 D is equal to D. S mu minus 1 is equal to half P mu plus K mu. And S mu D is equal to half P mu minus K mu. Okay, so claim, compute the commutation relations of these elements using those commutation relations up there. And when you do that, you will find that you get exactly the commutation relations of the first line for the group SOD comma 2. Is the claim clear? Is the claim clear? I'm not working out all this algebra here, it will take forever, right? Right, you can, yeah. But algebra is simple. I mean, what to do is clear. Is the claim clear? Okay. So the conformal group is SOD comma 2. That's sort of nice, right? It's some enlargement of SOD minus 1 comma 1, and you see the SOD minus 1 comma 1 living right in its heart. Okay? So if you wrote this as a matrix, with -1 here, mu here, and d here. You will get m here, and then mu -1, which is same as -1 mu. So that would be p plus k by 2. And then some minus of that. You know, this is determined by this, by antisymmetry up to the metric. Okay, whether it's plus or minus, I would have to think maybe plus of that. Okay, this guy -1d is d here up to some signs.
It is antisymmetric, right?
Not antisymmetric.
SAB is antisymmetric.
Not antisymmetric, because there's antisymmetric up to eta. SOD d plus 2 would be antisymmetric. Okay, here the relation that is obeyed is A eta plus eta A transpose is equal to 0. Right, so it's parts of it are antisymmetric, parts of, it's whatever this relation tells you. Okay, fine, and this part was the p minus k. I'm not keeping track of signs in any careful way. Okay, so that's roughly the structure. That's how the conformal group fits into SOD, 2. Okay, that's the next thing I wanted to tell you about. Finally, there is one more thing I want to tell you. Finally, there is one more thing I wanted to tell you, and that is this. We have been talking so far about Weyl invariant theories defined in Lorentzian space. And of course, physics always happens in Lorentzian space. For the study of quantum field theory, Euclidean space is a tool. It's a bit more than a tool if you're computing finite temperature partition functions, because those then just are Euclidean. But if you want to compute something in Lorentzian space, Euclidean space is a tool. It's never the thing you're interested in. It's just a mathematical tool to do integrals, right? Okay, but sometimes it's a useful mathematical tool because of analytic continuation. Sometimes it's useful to do analytic continuation in order to compute integrals more easily. Okay, so it is therefore sometimes useful, and I will tell you in what way it is useful in 2 minutes. Sometimes useful to consider the conformal algebra of a Euclidean d-dimensional theory. Okay, all that changes if you do this embedding. It's very similar. All that changes is that mu nu now is Euclidean. Okay, and so what we will get is an SO d plus 1, 1. Right? So the conformal algebra of a Euclidean theory is SO d plus 1, 1. This is clear. Very similar to the fact that SOD minus 1, 1 continues to SOD for Lorentz algebra. Okay. Now, in this Euclidean space, there is a nice way of thinking about what this K mu is. There is a nice way of thinking about what this K mu is. And to understand that, let's look at the following. Let's look at the following. Okay, consider the metric ds squared is equal to dx mu. Okay, now I'll make a coordinate change. Okay, I'll make a coordinate change which is, let y mu let me do it the other way around. Let x mu equals y mu by y square, by y alpha. Everything note is Cartesian and Euclidean. Up and down have no meaning. Eta mu. So the first thing tells you we're working in eta mu, right? Because dx mu dx mu. Oh, I'm sorry. I will not. Just eta. Not even eta, delta. Right, we're in Euclidean space. Okay, and just to highlight that, let me call it I. Okay, everything is Euclidean. So xi is equal to yj. Okay. Now let's compute the metric in the y coordinate. Okay. So the metric in the y coordinate is given just by plugging in. So dxi is equal to dyi divided by yj minus 1 by yj the whole thing squared. We'll call this y squared minus times 2 yj dyj into yi. Please check me if I've made a mistake. Looks okay, right? Okay. Okay. So let's compute dxi. Okay, so let's compute dxi. So this is equal to dyi by y square minus yi minus 2yi y dot dy by y to the 4 and then dotted with the self dyi by y square minus 2yi y dot dy by y to the 4. Okay, so we get two kinds of terms. There's a term which is dyi, and there is a term which is dyi, which is from here. Okay, so we'll write that out. That's dyi by y to the 4. That's the first term. Then there are the other kinds of terms which involve y dot dy. So let's take this with this. So that gives us plus 2y dot dy, the whole thing squared, divided by y to the 6. Now clearly the other one is the same. So that's 4. And then there is the term which is this times this. So but that is also this was minus, and then it's also plus 4 y dot dy the whole squared by y to the 6, because the y squared cancels one of y squared by y to the 8. Okay, so this is 0. What have we discovered? We've discovered that this inversion map, sometimes people like to write it with a minus sign. Xi is equal to minus yi by y squared. Would have made no difference to algebra. Two minus signs would have cancelled. Okay, that's a matter of choice. So this inversion map we've discovered is a map that under which the metric changes only up to an overall factor, namely 1 over y to the 4. Okay. So the inversion map is one of the symmetries of our theory, one of the coordinate transformations that will turn out to be a symmetry of our theory. It's not infinitesimal, it's a large one, but it's an interesting one. So one of the conformal transformations, one of the conformal coordinate changes of theory in flat space is inversion. You understand why I call this inversion, right? Because we're not changing the angle. What is x goes to yi by y squared? We're not changing the angle, but we're taking r to 1 by r. We're not changing n hat, but we're changing the radius to 1 by r. The people who like to do the minus say, well, we're not changing the angle, except we're doing it ulta, and we're making it half, 1 by r. Whether you do minus or not, that's up to you. Okay? So this inversion map is one of the conformal symmetries of our theory. Okay. Now, why did I tell you this? I told you this because there is a simple way to understand what a conformal, one of these cases. Claim. Go to the coordinate 1 by x. yi by y square I will often call 1 by x. Okay? So we could work in a theory which is Weyl invariant. In this coordinate, you have the same form of the action as in x. So now in this y coordinate, you can make a translation. So that's some coordinate change, which also leaves the theory unchanged. You'll get the same answers, correlation functions in this y after translation. Now we can view this coordinate back in terms of x. Okay? So what does this sequence of events amount to? Means invert, translate, and invert. Now let's make that translation infinitesimal. Invert, make an infinitesimal translation, and invert again. That will be some effective vector field in x. What is that effective vector field? Well, that's k mu. Not hard to check. Okay? So special conformal transformations are translations in 1 by x. Okay? So the statement that the theory is invariant under conformal transformations is equivalent to the following statement. The theory is invariant under scale transformations, Lorentz transformations, and inversions. Because if it's invariant under inversions, it's and the other things were true, then it's automatically invariant under special conformal transformations. So these are all the same thing. Of course, they're all in the end ways of just saying that it's invariant under all coordinate changes that change the metric only up to an overall Weyl scaling. That's why they're the same thing. All good?
Just doing inversion and then translation is also symmetry, right?
Just doing inversion and then, but that would be a large transformation. Yes, because inversion is a large transformation. We have to do it again if we want a small transformation. So that we want a generator. Right? Okay. Excellent. So, absolutely the last thing I will say about the conformal algebra is about an interesting hermiticity condition one can endow this algebra with. Okay? So, let's see. Consider a Lorentzian theory on S d minus 1 times time. Okay, suppose I'm interested in studying a conformal field theory in Lorentzian space on a sphere times time. So one quick comment about this already. Why might we be interested in studying a theory on such a weird space? Why not on good old flat space? Well, for various reasons, one of which is the following. Conformal field theories, by their very nature, are scale invariant. So suppose you ask the following question. What can you say about the spectrum, set of eigenstates, of a conformal field theory on Rd minus 1? Okay? The answer by scale invariance is obvious, is very clear. If there is any state with any non-zero energy, then there must be an energy with every non-zero energy. Because you can scale by scale transformations. So you see that scale invariance ensures that the spectrum of a conformal field theory is always a continuum. Okay? And in fact, even the scaling of the density of states is dictated very simply. Let's take a 1 minute diversion to understand this. How can the density of states be determined? Let's see.
Like whether it's continuous.
It is continuous, but when things are continuous, we're not satisfied by saying they're continuum. We want to know what is the density of states, right?
Okay.
How many states between E and? Even that is determined by scale invariance. 1 by E, no. Not bad, but not right. Any other guesses?
Like rho ED should be fixed.
Rho ED should be fixed. You're forgetting the volume. Consider a conformal field theory, some huge space. We'll put this volume as we imagine that there is a volume just thought of as a cutoff. Okay? Let's take it and put it at a finite temperature. Okay? So, the energy of that conformal field theory must scale like V t to the power d. I'm sorry, I switched between capital D and small d. V t to the power d. Why? Volume has dimension length to the power minus d minus 1. Length to the power d minus 1. So mass to the power minus of d minus 1. Energy has dimension of energy. So the final answer has to be of dimension energy. Now in a normal field theory, there may be some massive parameters that enter. Like a mass scale or some massive coupling constant. But in a conformal field theory, by definition, there are no parameters with length scale mass. Otherwise the theory would not be scale invariant. So nothing can appear in this answer other than temperature. And therefore, the only way we can get something of dimension energy is this.
Power of V is 1 just because of extensivity.
Because of extensivity. Because in any reasonable quantum field theory, energy scales like volume at fixed temperature. Same here as here as here as here. And that's the assumption. That is a reasonable field theory. Translational invariant state. Okay. What about the entropy of this theory? S, tell me how could it go? It's extensive, so this factor of V. What factor of temperature should I put? One of you. Yes. S has no dimension. It's a number. T to the power? D minus 1. What? E is equal to Ts. Okay. That I would have to think about. But this is clear. Okay. So now suppose I wanted not temperature as some thermodynamist's quantity, right? I want density of state, so entropy, as a function of energy. Well, I solve. I solve for, let's say, T here. So T is equal to E by V to the power 1 by D, and I put that in here. So I get S is equal to V times E by V to the power 1 by D. There are of course dimensionless numbers here that I'm not keeping track of. It could be a 2 or a 5 or a pi. All that I'm not keeping track of. Just keeping track of how things scale. Okay? To the power D minus 1. And so this goes like E to the power D minus 1 by D. And V to the power whatever. V to the power 1 by D, right? And therefore my density of states rho of E must scale like e to the power exponential of, because density of states is exponential of entropy, e to the power d minus 1 by d, v to the power 1 by d number. Notice, by the way, that d minus 1 by d is always a number less than 1. In 4-dimensional space, this is e to the power 3 quarters. Any conformal field theory, any scale in their theory, entropy scales like e to the power 3 quarters. Energy times 3 quarters. So if you express it in terms of energy density, then it will be volume times energy density to the power 3 quarters. Okay? Notice that it never scales faster than energy. Scaling like energy is called Hagedorn scaling, and is the borderline of well-behaved thermodynamics. Because if something scales exponentially, density scales exponentially, then thermodynamics is in danger, or higher, then thermodynamics starts breaking down. Because the partition function, which is rho of e, e to the power minus beta e, if this becomes e to the power s of e minus beta e d, and this e starts scaling larger than, s of e starts scaling larger than e, then this growth beats this decay and you get infinity. If s of e is exactly equal to e, then this is well defined up to a critical temperature, namely 1 over beta. This is what happens in string theory, as you know. Okay? So, quantum field theories. Fixed points of the renormalization group, the density of states always scales slower than in string theory. Always scales sub-Hagedorn. In fact, by this power. The argument was so trivial, right? But it's very important. These kind of things you must keep in mind. Okay, sorry, that was a diversion from where we wanted to go. Okay, so let's keep going. Let's keep going. So the reason I brought this up was that to say that if we wanted to understand the spectrum of the theory in flat space, it would always be a continuum. We will always know beforehand what the density of states is, up to some number. So the information about the spectrum is very trivial, some number. Okay? Related to this, theories on in flat space, it's hard. Okay, let's stop here. Let's stop here. Okay. On the other hand, if you take the theory on a sphere and you ask for the spectrum of a conformal field theory on the sphere, the answer to that question is a rich and interesting one. And how rich and how interesting will become clear in a minute. Okay? So let's. So this is my first offering of motivation for why we want to study this theory on a sphere. You might ask, why a sphere, why not a torus? It will soon become clear. Okay, so I'm studying this theory on a sphere. I'm studying the theory on a sphere, and this is the theory I want to study. But for mathematical purposes, I sometimes find it convenient to analytically continue time to Euclidean time. So now I have S d minus 1 times R. Okay? Now, what can I say about the space S d minus 1 times R? Consider dxi, just Rd. And let's view the space in polar coordinates. So this is same as dr squared plus r squared d omega d minus 1 square. This you all know very well. which I can rewrite if I want to as r square into dr squared by r squared plus d omega d minus 1 the whole thing square. Notice therefore that up to a Weyl factor, namely r square, Rd is the same as Sd minus 1 times r. Why is this r? Because then I can make the change of coordinates. R is equal to e to the power tau. And in this becomes e to the power 2 tau into d tau squared plus d omega d minus 1 the whole thing squared. And that's Sd minus 1 times time. Okay, so Sd minus 1 times time is up to this Weyl scaling, same as Rd. Okay, so in Euclidean space, even though I thought I was studying the theory on Sd minus 1 times r, it's the same thing as studying it on Rd. Right, because they're conformally equivalent, Weyl equivalent spaces. Is this clear? Now let's look to see how this Rd, maps to this Sd minus 1. Well, look at it. Radius of Sd minus 1, we wrote it as e to the power tau. And that tau becomes the time on this Sd minus 1. Time in Sd minus 1 times time, Euclidean time. And so you see the spheres map to the spheres here, whereas this radius r is equal to e to the power tau. Late times, big sphere. Very early times, a small sphere. Clear? Okay, so if we want to study a theory on Sd minus 1, this was the real reason to study on Sd minus 1 rather than, let's say, a torus. Okay, if we want to study the theory on Sd minus 1 times time, we continue to Euclidean space, that's a trick. Then we realize that trick is, once we've done that trick, it's same as studying that Euclidean theory on Rd. Okay? The other thing we realize is that there is this location, namely t equals minus infinity, in which spheres shrink down to a point. This is the heart of the state operator map, which unless somebody asks me about, I won't review for you. Everyone who was in my string theory class knows all about it. Okay, I won't review for you, it'll take time, but of course if somebody has a question, we'll go through it. Okay, there's the state operator map. So states of the Lorentzian theory on R, Sd minus 1 times time, map to local operators in the Euclidean theory on Rd. Okay, so there is a one-to-one map between the spectrum, and also you've already seen that translation in time on Sd minus 1. R dr is d tau under this map. That's clear? So translation in time on Sd minus 1 is scaling on Rd. And therefore the spectrum of local operators on Rd maps the spectrum of states on Sd minus 1, but the energy of the state on Sd minus 1 mapping to the scaling dimension of the local operator on Rd. Okay, so the spectrum of the theory on Sd minus 1 has very interesting interpretation. It's the spectrum of scaling dimensions of the theory on Rd. But now, once we set spectrum of scaling dimensions of local operators, we can drop the word on Rd. Because spectrum of scaling dimensions of local operators is a local statement, doesn't matter where you are. Okay, so that's another reason to be interested in this theory on Sd minus 1. Its spectrum has really interesting interpretation of spectrum of scaling dimensions of operators on Rd. Clear? Okay, now why have I told you all of this? I've told you all of this to motivate the Hermiticity a second set of Hermiticity relations. Okay, that are often very interesting and very useful for studying conformal field theories. And that is this. Suppose I want to study the Lorentzian quantum field theory on St minus 1 and times time, and it has usual hermiticity properties in Lorentzian space. Okay? Complex conjugation is the usual complex conjugation in Lorentzian space on this space. Now I analytically continue to Euclidean space. When I analytically continue to Euclidean space, tau has gone to I tau. I mean, there's an I between the two times. So what was Lorentzian continuation, what was complex conjugation in Lorentzian space becomes complex conjugation in Euclidean space plus the by-hand replacement of t by minus t. Because if we had an I times t, complex conjugation would have made it minus I times t. But once we do the analytic continuation, that doesn't happen anymore automatically by complex conjugation. But we want to mimic what's happening in Lorentzian space, because always, as we said before while studying spinors, always the complex conjugation properties of our theory are always dictated in Lorentzian space. And then they become what they become in Euclidean space. So complex conjugation in Euclidean space then, the one that is the analytic continuation of the complex conjugation in Lorentzian space, is complex conjugation plus flipping t to minus t. Okay? But flipping t to minus t, once we go to the plane, is flipping r to 1 by r. Not changing angles, but flipping r to 1 by r. Now what's the other name of flipping r to 1 by r, but not changing angles? Inversion. So complex conjugation, so if we want to take the complex conjugation of the theory in Lorentzian space on St minus 1 times time and bring it to the Euclidean theory on Rd, that complex conjugation is complex conjugation plus inversion. Okay? But you see, inversion is what interchanged momentum and k. Right? Because momentum was translation and k was translation after an inversion. And so, if you go through this logic in your head, you will find that the complex conjugate of this, the killing vector field for momentum, if you were studying the theory, the Lorentzian theory on St minus 1 and continuing its reality properties, P mu dagger is equal to K mu. Okay. On the other hand, mu nu dagger is mu nu. Because mu nu was just rotations on Sd minus 1. Nothing funny happening. Okay. So there is this way of thinking of physics, okay, suggests a second set of hermiticity conditions that one can put on a Euclidean theory, Euclidean conformal theory on Rd. There is another set, of course, which is start with the Lorentzian theory on Rd and then analytically continue Cartesian time to Euclidean time. Okay? That will make complex conjugation plus inversion of t to minus t. Okay? And then that will basically take P0 to dagger to, minus P0. But nothing else, nothing very interesting. Okay? So there are two sets of natural hermiticity conditions one can put on the conformal algebra. Okay, the Euclidean conformal algebra. Both of them descended from Lorentzian theories. One set will not give you anything very interesting because quantization with that set is guaranteed to give you a continuum. That's when you study the Lorentzian theory on Rd. The second set is going to give you something interesting Because quantization with that hermiticity condition, same as studying the Lorentzian theory on SD minus 1. And representation theory then will be very rich. Because you have discrete states, and the representation theory basically captures the operator content of the theory. Okay? Go on.
Why does this logic doesn't work in SD? Is it because we have curvature on SD and that is a length scale?
What you say, why don't we?
This logic of
This thing? It's because the SD has finite size.
so size of.
Meaning, we may be interested in temperatures which are of order that SD.
So that is a length scale.
That is a length scale, there's a curvature scale, there's a radius that could enter here. More, you see, when is extensivity correct? It's correct when temperatures are much larger than any length scale in the problem. I mean, much larger than the inverse length scale in the problem. Right? You won't get an answer that's proportional to volume at a temperature of order the radius of the sphere. Okay? Only when the temperature is much larger than the 1 over the radius of the sphere does extensivity take over. Okay? So extensivity is some asymptotic statement, which was always true in that case because V was a very large volume. It was a cutoff. It was true at every temperature. Is this clear? Excellent. So I'll just take 5 minutes more. I know we are over time, but 5 minutes more. There could be phase transitions, but even if there are not, it's going to be interesting thermodynamics. There'll be an interesting function of temperature, not something dictated by scale invariance. Because roughly speaking now, because there are two lengths, right? Temperature and R. So R times T is a dimensionless parameter. You could have an interesting function of that. Right? All clear? Excellent. Okay. The last thing I wanted to say is this. Just want to give you a bit of a flavor of this, and then we'll move on. We could have a whole 10-lecture course on representations of conformal and superconformal algebras. We don't have the time for that. Okay, I'm just giving you a bit of a flavor of some of this. Okay. The last thing I want to say is one little thing about representation theory. This, I told you, was the most non-trivial commutation relation of the conformal algebra. Okay? And now doing it without any signs and worrying about i's and minus signs very, very clearly, I'm going to, look. Suppose we wanted to find representations of this conformal algebra. This question is sort of like the question we addressed in the last class for representations of the supersymmetry algebra. But now you should be thinking of representations on the Hilbert space of states of the theory on SD minus 1. Okay? Suppose I want to find representations of this conformal algebra. Okay? Now let's see. You remember, we've got this theory on SD minus 1. And we're looking for the spectrum of energies. What are energies on this? This is same as D, scaling dimension, when we write the algebra on RD. Right, once we've gone to this Euclidean theory on RD, energy on this SD minus 1 was scaling dimension, because R del by del R was del tau. You remember that, right? So we're interested in finding that spectrum of scaling dimensions of that algebra, equivalently spectrum of energies on this sphere. Now, in any physical theory, we expect the spectrum of energies, and therefore scaling dimensions for operators, to have a lower limit. If the theory has arbitrarily low energy theories, it's a sick theory. It's low energy states, it's a sick theory. So on physical grounds, we expect the spectrum of energies to be bounded from below. Okay? Remember, spectrum of energy is the same as spectrum of D. And remember that the operator K carried negative scaling dimension. This was the same as the fact that its scaling vector had two x's but one del, unlike P, which had only a del. It had scaling dimension -1, unlike P, which has scaling dimension +1. So if we take a state and act with it on D, on that state with K, it lowers the SD-1 energy, equivalently scaling dimension, D, of that state. Is this clear? So if we keep acting K's on the state, we must eventually come to a state in which K annihilates it. Otherwise, it's got unbounded states which are energies unbounded from below. Okay? So the representation theory of this algebra then should be in terms of these modules. We should have these modules where there's a lowest state which is annihilated by all K's. These are called primary states. Or equivalently under state operator map, primary operators. Okay? And all of the states in this module are obtained by acting on the state with mu nu's, which don't change the energy, don't change the scaling dimension, or with p's, which increase the energy, equivalently scaling dimension, by 1. Now there's no limit to the number of times you can act with p. In operator language, p is just derivative. So you can take any operator and act with it on it by many derivatives. There's no limit to the number of derivatives you can act on p. So this module goes on forever. So this is what a representation of this superconformal of this conformal algebra is like. There's a module labeled by primary state. Primary state appears in some representation of SOD, because SOD doesn't change the energies. So it appears in some representation of SOD, and it's got a particular scaling dimension. So primary states are labeled by SOD dimension, sorry, SOD representation and a scaling dimension. Is this clear? Am I going too fast? This is clear, right? Okay. And then the whole module that is built on top of it is built by acting with p's on top of it. Great. Now, one can ask, what can one say? Are there any constraints on the scaling dimensions and representations of the primary states? Okay. Interestingly enough, there are such constraints. These constraints come from unitarity. Question: can these labels, these primary labels, be anything? Can you have any scaling dimension?
Level sense, delta and mu.
Delta and mu representations. Can they be anything, or are there some constraints? Okay. Yeah. Can I give you any numbers for these? Or there are some constraints? The answer is there are constraints. I finish, I know. And the way to see it is as follows. Take this equation. Okay, so let's say that I've got some primary state. This primary state has some scaling dimension, and it has some labels because it transforms in an mu nu representation. I won't call it P, I'll call it, I don't know. So let's say that there are some labels, mu, which are the representation labels, and epsilon, which is the scaling dimension. Now, I act with, let's not call it mu, let's call it theta. I don't know, A. Yes?
Would one say that from that combination relation, since P is scale accurate, the right hand side has to be positive?
Exactly.
And so there has to be a boundary.
Exactly. That's what I'm going to try to say here. Exactly. Okay. Now, let's act on this state by a p mu. Okay? And I'll put a number index here, alpha mu p mu. Act with anything. Okay? Now the norm of this state should be positive. And therefore, A epsilon alpha mu star, and remember P mu is a vector, as a vector field is real, but when we star it, it becomes K mu. K times alpha nu P nu. Okay, and we could also, this alpha could have been an alpha mu A. Could have acted on any state, right? And this could have been an alpha, so A prime, yeah. So mu A alpha A prime epsilon alpha nu A prime. This has to be positive, has to be greater than or equal to 0. For all choices of these alpha mu A's and their complex conjugates. This is clear? This tells you that this object here as a matrix whose indices are A mu on one side and A prime nu on the other side. So M A mu A prime nu, this matrix has to be a positive definite matrix. All the eigenvalues of this matrix have to be positive numbers. That's clear? But we can work this out.
Sorry, aren't you taking the norm for one state?
I'm taking the norm for one state, but this norm here was, the state was characterized by this alpha A mu. And this had to be true for every choice of alpha. The only way that can work is that the matrix is positive definite, because that's what it means for a matrix to be positive definite. That if we dot it with some column on one side and the star of the column on the other side, for every column it's positive. Okay? But what can we say about this M A mu A prime nu? We use the commutation relations, as Siddharth guessed. Okay? So ignoring various things. First we'll get eta mu nu times d, but that's just epsilon. So we get eta mu nu times epsilon times A prime. So that will give us a delta A prime. That's one term. And the second term we will get will be there M mu nu, okay, A prime. Now this quantity has to be positive definite. The first matrix was just identity. This matrix is in some tensor product space, and the matrix was just identity. Okay, so it's identity times epsilon. The second matrix is interesting. Okay, the second matrix, if you think about it, is the matrix acting on, so what is the space it's acting on? It's a space that is labeled by A and mu. Okay, and this matrix, if you think about it, is the dot product of the mu nu matrix acting on this tensor. It's mu nu times mu nu. It's like a j dot j term acting on the two states. It's like a tensor product space with a j dot j, and therefore can be written as m1 plus m2 the whole thing squared minus m1 squared minus m2 squared by 2. On the first space, mu nu is represented by just a vector, just the vector representations. On the second space, we have whatever representations we have. So what we get is an eigenvalue which is Casimir squared of whatever representation you can get by coupling vector to your original representation. Minus Casimir squared of vector minus Casimir squared of original representation. Okay, I know I've said this very fast. I could give you more detail next time. But in the interest of lunch, I'll end in 1 minute. So when you do that, you see the eigenvalues of this matrix are just determined by group theory. What you do is to take the lowest of these eigenvalues, the one that is most dangerous. Epsilon comes with a positive. The group theory stuff comes with a negative. Okay, I mean, you can find in that list of representations things that will come with a negative. And that combination has to be positive. Okay? Therefore, you're forced by a condition to say that epsilon is greater than or equal to something, which is a function of which representation? SOD representation, your states transforming. Let me tell you the answer for the simplest case. When you work this out carefully at level 1, when you work this out carefully in the three-dimensional conformal algebra, SO 3, 2, your epsilon is greater than or equal to L plus 1. See, in 3 dimensions, SOD is SO3. SO3 is SU2. This is the algebra we know and love, right? Its representations are labeled by an angular momentum L. Labeled by an angular momentum L. That's the L that I've written here. Okay, and epsilon turns out is equal to greater than or equal to L plus 1. Okay, this is true actually for L1 and greater. Something special holds for L equals 0 and L equals half. That's a whole rich story. SO4 has more interesting representations, more interesting such relations, and so on. Now, I've only worked this out for you. I've only sort of indicated how this works out at level 1. Meaning, I looked at states which were the primary and I acted on them with 1p, and I demanded that that the inner product be positive definite. But now I could also act with 2 p's, or 3 p's, or 4 p's, and make this demand. And you might worry that you get new conditions at each level. This has been studied in great detail, in particular by people before me, but also it's reviewed in my paper. And you can prove that you never get any new conditions above level 2. And the only place where you get new conditions is at level 2 is when you're dealing with a scalar. Okay, so you can find the whole set of constraints that come from unitarity on representations of the conformal algebra. The important thing is that unitarity gives you a bound which tells you scaling dimension, same as energy, is greater than or equal to some function of representation. These bounds are all known and are tabulated, for instance, in my paper. Okay, at the time I wrote my paper, everything was more or less known for the conformal algebra. What was not known was the equivalent things for the superconformal algebra. I'll tell you how that works next class. Okay, any quick questions or comments?
How did you convert that matrix to this commutator?
How did I convert this matrix? I'm sorry, I forgot to tell you that, you see, the commutator has the term which is p times k, but k annihilates the primary state. And therefore, this matrix products. Okay, excellent. Excellent. Any other questions?
So these primary states are graded with this L, like
Labeled by L. A particular primary state is in some finite dimensional representation of SOD. In the case SOD is SO3, the finite dimensional representations are labeled by J or L. Do you understand?
Yeah. No, I'm just saying, let's say state with epsilon and L plus 1. These are the data.
What is L plus 1?
Primary. This is the Muni charges, right?
Yes.
So then you create a state which is like its primary state. This is like on the edge of this state. And of this inequality, that is scaling dimension is delta and charge is L plus 1. And now you want to...
When that happens, okay.
I mean, I am saying, is it consistent with increasing delta, not increasing L? Is there any...
I know what you mean. Schumann is asking the following. He's saying, suppose you take a state which is some L and some epsilon. You take the level 1 states. Can you decompose those level 1 states into representations of epsilon, scaling dimension, which is of course epsilon plus 1, but decompose it into representations of SOD. And that's this Clebsch-Gordon. You get what you get by Clebsch-Gordoning 1 with a vector with the representation. Now, when you're on the edge, one of those representations develops 0 norm. And that's why this is interesting. These are like BPS representations. Okay, we'll discuss this further next.